Hello, everybody. Welcome to the Grace Code first day. I'm Karim Azum, and today with Pierre from the lab, we are going to present a webinar dedicated to modern C++ for CPU computing. As you know, we have several webinars until the summer school, so we invite you to join us for the webinar, but also for the Grace Code School. You need to register for that. You can join us at the lab if you want to come and to participate to the Grace Code School with the teacher, but also on several satellite sites everywhere in Europe. But also you can join us online. But for that, you need to register first. If you want to become a satellite site, I'm here also to discuss with you. So now we are going to start the webinar with Pierre. Pierre, if you want to start.
Thank you, Karim, for the nice introduction. So today we will speak about STD algorithms, so all the new wizardry that we can do with modern C++. So to start this introduction, I will start with a main problem that we want to achieve especially if you want to have some performances. So we start everything with an application. And for what concerns us, the first thing that we want to have is performances. So you have to take care of your caches, of your vectorization, of everything that we already discussed, but we will dig a bit more in this presentation about this subject. But that's the first topic only. And then once you have performances, at some point you want to have scalability. So it's quite a bit more difficult to have that because, of course, you need to split your data well. You need to split your computing. You need to have maybe some data exchange, and it's not really simple to do. On top of that, once you try to have some scalability, you want also to have some portability. So you want to use several CPU vendors and several GPU vendors, and it's not really easy, and you don't have the same loop ordering, stuff like this. So you have to be careful on that. And the most difficult part that we have on all this topic is we also want to write as less code as possible. Because if we develop less as possible, it's easier to maintain. And if it's easier to maintain, it's easier also, it's more flexible if you want to add some functionality. You don't have to duplicate the work anytime you want to add one kernel in your application. So to do that, we will express parallelize first, because of course, everything starts with a design. So let's pretend for this purpose that we want to treat some event. And we are lucky, so we have lots of events, and they are all stochastic, so they are independent. So we can say, okay, let's treat one event per thread, for example, but maybe it's not enough. Maybe they don't fit in the memory, maybe they don't fit in the cache, so maybe you have to break down your event a bit more. So to do that, you have to think, okay, what is a smaller brick inside of my event? In this case, we analyze some data, so maybe it will be some captors. So let's say it's pixels or calorimeter, lines, stuff like this. But maybe it's still not enough, and you want to break down another part, and maybe your pixels will have a times response, so pulses, waveforms, or slices. And for that, so we have a big tensor of parallel data, and we have to ask ourselves in which order we want to store the data, because of course the ordering will matter in terms of computing, in terms of performances. So first, to answer this question, we have to ask ourselves, okay, what do we want to do with this data? And the first step may be, generally this one, it's the calibration. So roughly we get some voltages in input, and we want to transform them into number of photons or energy or in a calorimeter, stuff like this. So let's pretend for this particular example that the calibration is independent in terms of performances of the ordering of the tensor. So of course, normally it's not really the case, but let's pretend it for the purpose of this slide. And once I said it's independent, it's whatever the ordering, you get the best performances, not the same performances, the best performances that you can have. Otherwise, of course, you have to change. So, okay, let's pretend this is independent. So what is the second step of the analysis? So maybe in this case, it will be a reduction. So we integrate the slices here to get one value. We can also do a weighted sum, no problem. But basically, this will be a reduction. And to optimize a reduction, you need to think about back dependency. So if I want to sum this element to this one and to this one and to this one, etc., I want to be sure that this element will not be contiguous in memory. So naturally, I want to have another axis to store my data. So this one, so I can sum this full row to this full row to this one, etc., and everything will be efficient. So I can vectorize this computation. It's okay. I can vectorize the integration, so the reduction, which is what I want to do. And I vectorize also the calibration because the calibration does not care in that case. The second axis will be logically this one, because I want to have my rows not too far in memory to treat the same event. And the first axis will be the axis of the event, of course, because it's the last one we have to deal with. So the last axis will be this one, the second this one, and the third this one. On the event, I can parallelize on everything I want. So on cores, on nodes, on clusters, because all the events are stochastic. So whatever the order, it's okay. And the most important thing here is to remind you that computing drives data storage. You cannot randomly store your data and hope for the best. It's not possible. You have to think about what you want to do with your data to be sure that you have the faster computing possible. So once we did that, and since it's a C++ webinar, we can try to do some computing. So if I want to compute on CPU, I can use maybe TBB, Threading Building Blocks, the parallel library of Intel. If I want to compute on GPU, I can use Thrust, I can use CUDA, I can use the HPC SDK, I can use HIP, I can use lots of dedicated vendor library. And we have a lot of library to do a bit of both. So Cocos, Alpaca, Cycle, OpenCL, OpenSCC, so you can do both. It's not really trivial to do both, but you can do both, and it's really efficient. But we will try to move a step further in this webinar. And we will remind us that if we use the compilers, so G++, Clang++, stuff like this, they are able directly, if you do some C++17, to call directly TBB for you. So you don't have to care about how to call the library, which parameter. Everything is handled that under the hood by the compiler itself. And the point is, on the GPU, NVC++ is capable to do the same since 2020, late 2020, October, November 2020, for you. So you call C++17 functions, and then you are able to call directly Thrust and Cube under the hood, and everything will be efficient, and you don't have to worry about that. So of course, we will talk about the CPU part today, and the GPU part will be a bit later in a couple of weeks. So it's a standard unification, and it's really interesting, and I will try to present that to you today. So let's start with an Adama product, because of course it's one of my presentations. So of course there will be an Adama product somewhere. So it's an element-wise operation. And if I write some C++, classic C++, I will get this kind of for loop. So I get an index and I compute my element one by one, and everything is okay. The first remark that we can do here is we don't really need to have an explicit order because all the elements are independent. So if I compute the first one and then the fourth one and then the second one, it's not a problem. At the end of the day, if I get all my results, no problem. The ordering does not matter. So this explicit order is not necessary, in fact. And to answer this question, people of C++ came with STD transform, so to express the fact that we don't care of this ordering, but it's not that used because it's a bit complex, of course. You have tab X here, you have begin and end, you get your tab Y, you get the result, and then you pass a lambda and you do everything you want in the lambda. Not that useful, but since C++ 17, we have std transform with an extra parameter, which is the execution policy. You can tell the compiler directly how you want to execute this particular lambda. And in the execution policy, you can say, okay, I want sequential execution, the same of the for loop above, or you can say I want unsequential execution, so it's not vectorized, it's out of order, unsequential, so you can do other trick also. You have parallelize execution, so with TBB, for example, in terms of threads, and par unsec to have parallelize and non-sequential execution, so potentially parallelize and vectorize execution. So it's quite nice, and you can call the compiler directly to vectorize like this. But before, we will explain also what is vectorization. And I will explain to you what is vectorization and how to vectorize in the old fashion to make sure that you will understand what the big improvement that we have with std algorithm. So vectorization, basically, the point is to compute several elements at the same time on the same CPU cores. So basically, if I want to do a scalar computation, I get my two operands, I do my operation with my operands and get a result. It takes time, and I get one result. If I do the same on bunch of elements, so here, vector of 8 elements, I can do the same at the same time. So bunch of 8 with another bunch of 8, I do my operation, the same operation for the 8 element each time, and then I get 8 results, and it's really efficient. So we get a natural speed up by doing that. So we have to be efficient, of course, but it's quite okay. So to vectorize, it starts to be a bit old now. In 2007, we have SCC4, so we can vectorize 4 elements at the same time. AVX 2011, 8 elements at the same time. AVX2 2013, 8 elements at the same time. And AVX 512, 2016, 16 elements at the same time. If you want to know what is the capability of your processor, you can ask on Linux cat proc CPU info, and you get the flag of the CPU, so you can grep AVX, for example, if you want to search for AVX and the AVX family. And on Mac, you can do the same with a sysctl-a, and you can grep the matchdep CPU to get the information. Of course, it's not the same if you get an Intel processor, if you have a M1, M2, M3 processor, but you can get the information like this. And of course, it's not as simple as this, because here I spoke about float 32. For integer 32, it's also 4 elements for SSC4, but the point is for AVX, it's only 4. So if you want to vectorize a bit by hand because you want to force the compiler to vectorize, you have a weird middle here, because you have 8 for float, but you have 4 elements for integer. And if you want to do some masking, it's quite annoying, in fact. For AVX2, you get the same size for the integer and for the float. And for AVX 512, I will not go into the detail because we have 20 extensions, so it's a bit too much for this webinar. So first, when we vectorize, we want to have data contiguousness. So basically, I want to have the same type of data in my vector. First step. Of course, if I don't have the same data, I will have some problem with vectorization. And basically, if I get a vector register, I don't have the same element in my register, I cannot vectorize. If they don't have the same type, I cannot vectorize. But it's not always a matter of type. You can also be sure that the meaning of your data is the same. So for example, if you have vector x, y, and z, and you want to vectorize the computation because you have lots of particles, for example, lots of points, whatever, you don't want to mix x, y, and z because they don't mean the same thing. And at some point, if you want to mix the components because you want to do some cross products, some dot products, some stuff like this, you will be stuck and you will not be able to vectorize. So you have to separate even if the type is the same because the meaning is not the same. Then once we have contiguous data, we need to align the data with the vector register. So for example, here 8 plot 32 on AVX. So I have aligned data here, border of aligned data, and if I align my vector well, I will be able to compute faster and to vectorize all the elements here. So in my example here, let's pretend it's 3 cycles. Now it's a bit faster with the last architecture, but let's pretend it's 1 cycle per computation. It's easier to compute like this. But today it's a bit faster, of course. It's maybe 1.5 cycles, stuff like this, as Adrien said in his presentation. So this is a happy path. Then if I don't align my data, I will have a problem. So I still can vectorize some part of my vector. So here I get 1/8 of cycle per element for a computation in AVX, for example. But I have to deal with the first part. So we call that a pill. So I will have to consume element by element in a scalar way until I reach a border of aligned data, vectorized data, vectorizable data, if you want. And it's the same for the last one. We call that the tail, and we consume the last element because we cannot fit a vector register here. So we have to do it one by one. So these are scalar computations. So it's about 1 cycle per element, as I mentioned before. And the problem here is we'll have 10 cycles to do the same computing. So more than 3 times slower, which is quite annoying in that case. So to mitigate that, we can also have some trick. We can add a padding, for example. So to be sure that the last part of my vector will be treated in 1 cycle only and not 3 in that case. So of course, I need to use neutral value for the operation. So here, if I do some addition, subtraction, or multiplication, 0, it's okay. But of course, for division, I will have some problem. So I don't want to do that. Maybe 1 is better for division, but also, as Adrien said, division is slower than the other operations. So maybe you want to multiply by the invert, and then 0, it's okay, because you multiply by the invert. So with this trick, I can have only 8 cycles to do the computing with the padding. So if your vector is not exactly a multiple of 8 in that case, or 16 or 4, depending on your architecture, you can mitigate that. And to align your data, you need to change the allocator. So not malloc or not new, but memoline, POSIX memoline, std align malloc in C++17, which is really powerful. Or you can also, as Adrien mentioned, use in std vector, you can pass a dedicated allocator, a custom allocator for whatever you want. So here we can pass an allocator to align data in our vector. And then, of course, it's better to use a type def because you don't want to have a long type in your library. So it's better to use a type def for that. And here it's okay. But it's not the end yet, because we align our data, but then we have to tell the compiler that the data will not overlap. So the restrict keyword is made for that. So here, my restrict, I don't have the restrict. So the compiler might think that maybe tab X and tab Y will overlap at some point, because there is no guarantee here in the definition of the type. So the compiler will not vectorize in this case. Here, I use the restrict keyword. So the compiler will say, okay, you promised me that table will not overlap, so I will try to vectorize, I will try to optimize everything. Of course, if you are lying to the compiler, you will have a segmentation fault, but that's the price to pay to have faster execution here. Once it's done, we align data, but then we need to tell the compiler that we have aligned data, because where you align data, when you allocate data and when you use them, it's not the same. So you have in your function to tell the compiler, okay, it's multi-assume align. So that's the intrinsic function of the compiler to tell the compiler that the pointer here is aligned. So I swear my pointer is a line. Or you can use std assume a line in C++17. It's much better also to use this one. And again, if you lie to the compiler, you will get a segmentation fault. Here, vector alignment is a macro. Of course, it's better to have some trick automatic to get the alignment, but maybe you know the machine on which you will run, so not a problem. So here, I assume it will be AVX or AVX2. So I say my alignment will be 32 bytes. It will be 64 for AVX512, for example. So you have library to get that automatically, but I will not go into the detail for that. So here I get my align data. And then finally, I have to pass specific option to the compiler to make sure that everything will be vectorized. So first, F3 vectorize to activate the vectorization explicitly for G++, for example. march equal native to tell the compiler, okay, target only the host CPU for the binary, so not make the binary compatible with everyone by default, just this one. So with this particular microarchitecture. And the same for mtune equal native. So you want to enable optimization only for the current CPU that you are running to. And AVX2 to enable explicitly the AVX2 extension. So it's not needed anymore with G++11 or Clang++ 14, and of course the newer version after that. But I like to keep it to remind me that, okay, it's this particular architecture in my command line, otherwise you don't really know. And if you have some runners, some GitLab CI, stuff like this, you have to keep track of what was the architecture of your machine. So it's quite interesting to have that also in mind. So to summarize, you need to have a custom malloc. So here an asterisk malloc for an old school, but of course you can use POSIX memoline, and std align malloc. Then you have to use restrict keywords to swear to the compiler that everything will be independent. Then you have to tell the compiler that everything will be aligned, and then you have to pass the proper argument to be sure that everything will be vectorized. And the compiler will try to vectorize. So in terms of corrections, so we have the for loop here, and I have to just tell the compiler that my vector will be aligned, my pointer will be aligned, and the restrict keyword here to tell the compiler that I will not have overlap on the table. So if I do that, I compare to Adama Product 03, classic 03 optimization. I have the vectorize, so the vectorize by hand, as I mentioned before. So vectorize with the for loop, with the built-in assume line, with everything. And now I can compare to the Adama Product unsec 03, so not vectorize, but quite fast. So we get roughly the same performances here, totally normal. Then if I use the unsec with vectorization, so the same option, you have to pass the option anyway, it's not magic, then I get the same performances of my for loop, but it's handled by the compiler itself. And notice that I don't have to tell the compiler that the data are aligned, the data do not overlap. It's implicit by calling the transform. You pass a contract, an API contract with the compiler to tell, okay, I pass only independent vectors in that API. So it's okay. You get nice performances. And if you try to have aligned data, so with a custom allocator on the vector, you get also really nice performances here. So it's a really good point. So if I compare G++11 and Clang 14, of course, we'll use much recent compiler later, but let's try with this one because we get the same performances roughly to the last ones. So here, O0 is the same, but there is no optimization, so quite normal. O1 it's the same also, and then O2, O3, and OFAST are faster on Clang and slower on G++. But the point is, G++ is really conservative. So if you don't explicitly tell G++ to vectorize, there is really few chances that you will vectorize, in fact. But Clang as you ask for O2, Clang will try to vectorize partially. So it's a partial vectorization here. So on AVX2, you vectorize in SSE4 because you have the guarantee that data are aligned on SSE4 boundaries, but not AVX. So I'm not telling you here that Clang is better than G++. I'm just telling you that they disagree on what is O2, O3, and OFAST flags. So here they disagree. So G++11, I don't ask him to vectorize. There is no vectorization. Clang, I don't ask him to vectorize, but there is partial vectorization. Of course, if I have the full options, I will get the same performances for the two, because of course, once you get the best performances you can, you get the best performances you can. And here you have the partial vectorization here, the full vectorization here for the two. Then you have the unsec vectorize here, the vectorize align, which is quite better also here in this case. So it's quite important also to think about that. You are not obliged to align everything if it's not possible. You can have like nice speed up if you do not, but if you do, it's quite nice to think about that. So let's move on a bit to SAXP. So single precision AX plus Y, or DAXP, double precision AX plus Y. So it's a kind of words vocabulary that we'll have if you use BLAS. So BLAS, LAPAC, MKL, stuff like this. So it's still an element fuzz operation. We can do a for loop like this. As before, we don't care about the explicit order because all the elements are independent. We can do that for C++ with an entity transform, and we need to catch the A variable by copy to be able to put it inside the lambda. So it's lambda wizardry of C++. And finally, we get the last STD transform. So with the execution policy, with sec, unsec, parent, sec, as before. If we do that in G++ and in Clang, we get roughly the same performances, and Clang also tries to do extra stuff in O2, O3, and OFAST that G++ will not try because of the complexity of the loop and because you don't ask G++ to vectorize, so there is no vectorization as before. If I try to vectorize fully, I will get again the same performances here, roughly. And here you notice also the O2 and O3. O2, there is a partial vectorization yet that you don't have here because, of course, you don't ask for the optimization. And by the way, of course, this step comes from the difference that we have here. Here we are in the L1 cache, and here we are in the L2 cache. And since SAXPy and Adama product are memory bound, we have a step. That's really, really simple. So let's try to do some extra stuff. So now reduction. Reduction, we have a vector. We want to sum all the elements to the vector to one scalar. Really simple. So we can write this kind of for loop. And every time you want to write this kind of for loop, you have to think about Vincent on this precision webinar, because of course, if you do that only with floating points and you have a lot of elements, millions of elements, you will have a problem of accuracy at the end. So don't do that. Here, I'm doing that because I know I will sum only few thousand of elements, not much. And I know also my data are well conditioned. So I will not have big value with really small values and stuff like this. Everyone is well conditioned and I don't have too much value. So I can do this kind of stuff. And for the same reason, we will assume here that we do not need an explicit ordering. But of course, if your data are really badly conditioned, you need to sort before or use the compensated sum that we saw also in the Vincent webinar. So if you are curious about that, I invite you to see this webinar. It's really interesting to know what trick you can use once you want to do a sum, really big sum, but without losing the precision. So let's assume we are in a happy path. Everything is well conditioned. We don't have too much data to sum. Everything will be okay. So here I can say, okay, I can do a std reduce with parentsec, for example. So I get my begin and my end of my vector x. I start to sum from 0, because you can start to sum from everything you want. And then I use std plus because I want to sum my values. Of course, you can do a reduction with every operator you want. Here, it's a plus. It's quite common to have an addition. So if I do that with G++ and Clang 14, so everyone is quite okay, but OFAST is a bit more aggressive in Clang than in G++ 11. And of course, as always, if I try to vectorize, I will get the same performances. So these are the same performances for the for loop, the classic for loop with the accumulator. And you get the same performances from G++ 11 to G++ 15. I recheck last week, everything is quite the same. So here it's my classic for loop. What happened if I try to do the reduction with intrinsic functions? So by hand, I force the compiler to vectorize. I get speed up of 5 to 10, which is quite big, in fact. Okay, so there is a problem with the for loop. What happened with std reduce? Oh, the std reduce is quite close to what I did with my intrinsic function, even faster. So yeah, it's a really good point for std reduce. With the unsec version, of course, we get much faster reduction. So 10x compared to the classic for loop. So if you have a lot of for loop in your program, replace them with std reduce, and you will have a faster result. Of course, if you can unorder the sum, otherwise you will have a wrong result if your data are not well conditioned. Okay, it's a nice point, but of course I don't want to stop here because the compiler beat me, and it's not quite okay for me. So I can use some tricks to beat the compiler again, and I will explain to you how to do that. So first, for loop versus std reduce. So what's going on? Why for loop is slower than std reduce? So if I get an explicit ordering with my for loop, with my reduction, in scalar mode, I will start with one accumulator equal to 0 here, and then I will loop and we get my next data, sum my accumulator to it, and put the value inside my accumulator here, and everything is okay. At the end of the day, I get my accumulator with all the values, with also potentially some problem of precision if I have too much element, but we are in the case where it's not a problem. For the unsequential execution, it's a bit different. Here we'll have a vector accumulator. So here I vectorize only 4 because it's about the size of the slide, but of course you can vectorize. Here it's 8 times for AVX, 16 times for AVX512, etc. So here I loop. I have my vector accumulator. I get lots of full vector of value at the same time. I sum everyone in one cycle, in one step, if you want, and then I get my result, my accumulator. I reduce my vector into one element, so it's horizontal reduce, we can call that. And then I get the same value here and here. Even a much precise value, because here I sum maybe 1000 elements in one accumulator. Here 1000 with 4 accumulators, so I can mitigate the problem of the precision, as Vincent mentioned also in his presentation. So here I have a fully vectorized reduction, and if I try to vectorize, what the compilator does. So here I start with my accumulator, a scalar accumulator as I designed here. Here is the scalar accumulator. Okay. Then I will vectorize load my value, not always, in fact, depending on what you do. Even with C++ 15, sometimes it's not vectorized. So you lose the vectorization already here. But sometimes it's vectorized. So you load 4 elements at the same time here, or 8 or whatever. So looks great. And then you have a reduction of the vector, so an horizontal reduction here. Because of the graph theory, the iteration should return a scalar, because here your iteration should return a scalar. So if I have a vector here, my iteration should return a scalar, so I have to reduce my vector to a scalar. And then I add the scalar to my previous accumulator, and I get my accumulator updated. And of course, this is really slow. You don't want to do that. You want to do that. But here, because of that, because of the graph theory, because maybe you don't want also to change the ordering, because if you explicit the ordering, maybe it's on purpose. So the compiler cannot tell, okay, there is a for loop, but I don't care of the for loop. Now, if there is a for loop, of course, compiler has to take care about the for loop. If you don't want this kind of stuff, you need to use this one. No, it was possible since G++11 stuff like this. You could have vectorize load, and now in G++15 it's not anymore the case. At least I did the check this morning to be sure, and it was not the case. And the last point is, once you have reduction, as I said before, we have back dependency. We always have to have a reflex to think about back dependency. So this means that I get my accumulators, scalar or vectorize, whatever the accumulator is. And then if I unroll the for loop a bit, just to see what's going on, I will sum some data here, some scalar data here, or I will sum some vector data here. Okay. But every time I want to compute the next one, I need to get the previous result. I need to wait for the previous result. And the problem is, once you want to optimize a reduction, every time you do some computation, you need to wait for a certain elapsed time until you can get the result and use the result back, as Adrien said in his CPU presentation. So even if you vectorize, you can vectorize your computation, you have to wait until a certain amount of time to get your result or to be able to use your result back. So if I use one accumulator, of course, it's quite a pity because I will pass my time to wait until I get the result. And of course, it's not optimized. So the trick is, if I use two accumulators, I'll be able to compute the sum of the first one, then I wait for the result, but then I can compute for a second one, not at the same time, because of course I have only one unit to do the addition here in my course, but I can do the computing in differ mode, and then I can wait also. And in my little schema here, if I have 4 accumulators, I get the peak performance of what I can do with my reduction here, and I can practically sum do one computation for each time until I can get the next one, and so I completely amortize the waiting time with computation by using other accumulators. So that's the why we get, if I get the classic vectorize with for loop, I can have my intrinsic, so as I said before, so I sum vector register to vector register, so the same strategy for the reduce. Then I can interleave twice, so with 2 accumulators. I can interleave 4 times with 4 accumulators, and notice that with 4 times G++ is really smarter than Clang and do a better optimization here, because it understands that, okay, we can maybe unroll 1 time to be sure that we reach the peak performances here, and Clang cannot do that here. And finally, if I interleave 8 times, so I get the best performances for Clang and the same performances as with 4 accumulator for G++, because G++ was a bit smarter on this topic. So that's for reduction optimization. So I spoke a lot about triadic. So triadic is X plus Y. So you have one operator, 2 operand, and then you compute the result and you put the result inside third operand. Okay. But of course, maybe we can have quadratic operation to compute and more, of course. And we need to have a way to do the optimization and to do the computing for that. So how can I do that? Of course, with a simple for loop. It's easy. It's as always. We don't need to deal with the ordering, but whatever. And in C++ 17, 20, and 23, we have this kind of stuff. So we can use a vector of index and iterate on a vector of index to do the computing. And then we can also have vector x, vector result, and then we can catch vec y and vec z to do the computing. So we have to catch them as std vectors, otherwise we will not have vectorized computing. But okay, why not? If it's the price to pay, why not? So if we do that, we have a fully vectorized result. We need an extra table, so it's not really elegant, but it was the old way of doing things, in fact. It's not vectorized if you use the std for each, so you have to use the std transform. For whatever reason, it's inside the standard library. And it's not vectorized if you pass pointers, vec x and vec y, to say, okay, I don't want to pay the copy because it's too expensive, so you will not have vectorization. Of course, there is another way to do that. It's std view transform. So if I have a bit different quadratic computation, so x times y times z, I have two solutions to write this in std view transform. I can do that. So I can get my view transform, std view, I zip x and y. So I get a tuple. I extract the tuple and I do my Adamar product with my tuple and I return the view here. And then I pass the view to an std transform with a parent sec, for example, or on sec or whatever you want. And then I walk to my view. I walk also to my vector z here. And here I get my xy result and I do my Adamar product with z. It's okay. Of course, since zip is really flexible in C++, you can do that. You can say, okay, let's zip x, y, and z in the same zip, because it's possible, no problem. Then I have x, y, and z in my tuple. I can extract them, and in my lambda function here, tell, okay, I just want to do the product of the three. Everything is fine, no problem. And then I pass the view to the std transform with the execution policy I want. Then I just return the result because I don't have much computation to do here. And I get my result. So the point is, it's quite elegant. We don't need an extra table. Like it's really good. Notice that with std view transform, you don't need to pass an execution policy, because if you declare a transform, it's just in terms of declaring a computing, but not performing it. So you declare that you want to perform an Adamar product, for example, here, but until you don't use it inside the std transform, you will not get computing. So you cannot pre-compute with view transform. Just once you call transform that we will have the real computation happening. So what are the performances of everything? So with G++15, which is really important because it's not possible with G++14, we get O2, which is not vectorized. Of course, it's O2. So as I said before, if you don't ask the compiler to vectorize, you don't have vectorization. Okay, that's normal. Here, if I ask Macao, it's not vectorized also. Even for the vectorized one, it's limited by throughput, and sometimes it's vectorized, but you get the same performances because of the copy, because of the vectors, and that's why the computation is horrible. Okay, quite annoying. This one is not vectorized, but we don't have data copy because it's the one with a pointer. So I pass pointers instead of vectors. So I get the same performances every time. So performance per element, so nanosecond per element. So it's quite stable, but it's not really fast. This one is vectorized, but it's a trick. The trick I did before last year, because of course it was not working. So I use a temporary vec x and y, and I use two std transform, once to perform the first part of the computing, so x times y, and then the second to perform the xy times z. Okay, so it's a bit of trick. It's not really elegant also. You have to split your computation. It's a bit heavy. it's much better to use views. And so the point is, all these previous ones are using index table, which is not really elegant. You have to allocate an extra table. It's not really vectorized. You don't have really nice performances. And the really good news of the presentation is now it's vectorized with view transform and view zip. At last, it's okay. It's working. So you can have your quadriadic operation or whatever you want operation vectorized well with std view transform with zip, so you can pass as many as a table as you want, and everything will be vectorized well. So it's really elegant. It's working. So it's C++23 only. So don't try to do that with C++20. Your compiler will complain a lot. So -- std equals C++23 and not C++20, and everything will be fine. So to conclude, in C++17, 20, and 23 algorithms, so it's really okay for triadic. If you want to use std transform, no problem. So you have transform, you have for each, you have reduce, you have min, max, you have 150 different kernels. So normally everything is okay for you if you want to have a look. And std view transform is vectorized with G++15 now. It's not the case with G++14 because the view zip is not vectorized. It's considered as contiguous data, even if they are not. So the compiler will not vectorize that before. Now it's vectorized. So use G++15 if you can. If you need to have this kind of stuff, it's really important. So as I mentioned, also it allows easier vectorization. So you don't have to worry about the line of your data, the contiguousness of your data, or the pointers, the allocation, everything. You just pass of course it's better if it's aligned, but if it's not, you will still get some performances. If your vector are not too short, of course, if the vector are really short, alignment really does matter. You can compute on CPU and GPU also, but the GPU will be for another part in a couple of weeks. I will show you how to do the same on GPU. And we expect also a huge improvement in C++26 with linear algebra. So it's still ongoing, it's still on work. Lots of functions are not documented. So we have lots of dead link right now in C++ reference. It's ongoing. So we'll see that once it will be usable. So thanks for your attention. And if you have some questions, don't hesitate to use the chat, and we'll try to answer all the questions at the end of the session. Thank you.
Thank you, Pierre. We have some questions.
Okay.
The first one is from Michael. He he could align vector load on x8664 even though it I don't understand really the question. Perhaps
Okay.
you can help me, Pierre.
Oh yeah. I didn't mention that. Yeah. If you want to have the best performances possible, you need to have aligned data to load. So you have the classic load, so the intrinsic load. You can also, since the very beginning, in fact, have unaligned load. So unaligned load historically has a little overhead because, of course, you don't have aligned data, so it's not as fast as this one. But now the penalty is really small on last architecture. So the AVX 512, stuff like this, the penalty is quite small, so it's not that a problem if it's not aligned. But depending on what you want to do, because here it's really simple computation, if you have a stencil, if you have stuff like this, could be a bit problematic. But yeah, if you have an old architecture, it will be a big problem because you will have a big penalty. Now it's not that bad. Yeah. That's a good remark. Yeah.
And we have also a question from Olivier. He asked about some example codes.
Yeah, all the examples are
provide.
online, or maybe I can show you. So it should be in this one normally. So it's in French because I didn't have time to translate everything. So if you go here, maybe I will put that in the chat.
The chat, yeah.
So you have all the examples of all the wizardry I just show you. So in C++ 23, you have zip, you have repeat, you have chunk, you have Cartesian product, you have lots of stuff. I don't have time to dig into everything, of course, because it's we have a lot of stuff. So it's in French. If you can read the French, it's okay. And so here you get the zip here, for example. So all the example I mentioned. So I should also, I'm trying also now to pass all the lecture into Pixie. So I have some examples. So reduction example and Aubert product are on Pixie, but not everyone, of course. And you get this kind of vector here. So I have the repeat here, for example. Why not? With the zip. And I do some computation. I try to vectorize and try to check the performances. I ask Macao also to be sure that everything is fine. So question from David. Maybe I missed it. But why do we have to pass an std vector and not a raw pointer to std transform slide 27? Yeah, it's for the API. I was also surprised, but yeah, if you pass a pointer, you don't have the guarantee that the pointer is a line. You don't have the guarantee that the pointer is independent. And again, you don't have the restrict, and the compiler cannot tell, okay, it's okay, I can vectorize. So that's why I think there is a problem, and there is not, it's not vectorized. With the allocator, yeah, it's not really the allocator, it's a restrict problem. Yeah, it's not the allocator, it's a restrict problem in that case. How about using stdspan? I didn't try with stdspan. Maybe it's better. You should try. Good point, really good point. I will try to use stdspan. So thanks for Michael. Or maybe you want to continue, Karim?
Yeah, you have another question from Mark. The question is about the link between ranges and view.
Okay. So in ranges, it's a trick to have a bunch of contiguous values. So you want a range for one element, one index to another, and the range will store the two. And in the for loop, you will get the whole range without the allocation. So it's a trick. And the view, it's you have a bunch of values, so a vector, or even a range, because a range is also a view. And you will manipulate your vector without copying the data. Just for it's a lazy. In fact it's a bit in Rust. You have the same stuff in Rust. So you do some wizardry with your iterator, and at the end the compiler will take the whole and simplify everything to do the computation. It's the same. It's just you tell the compiler that you want to do this kind of stuff. So the zip is the same. That's what it is, a view. And then you do the view, you do your trick, and then the compiler will get everything and optimize it well at the end. So yeah, it's quite close, but it's not exactly the same. Range is for a range of value. So from a start to an end. And view, it's more generic.
You have also another question from Maxim. The question is focused on latency and how latency is hidden in std reduce algorithm by using multiple accumulators, a parallel library that's used in the background or not?
There is TBB in the background. So of course, if you do this kind of magic, you need to have TBB, not only for the parallel part as I expected, but also for the vectorized part. So basically, yes, you can have this kind of stuff. When I have a look to the assembler, it was not clear that it was unrolled, or not interleaved at least, but maybe unrolled by the compiler itself. But the problem is, normally, once you unroll, you don't fix the problem of the back dependency. It's better to interleave. But the problem is, if you interleave, you break the graph or your computation, and the compiler cannot do that. Compiler is not able to do that. That's why also, if you remember the performances, this one here. Here you have Clang with 4 accumulator, and you have G++ with 4 accumulators, but with not the same performances because G++ unrolled automatically here one time because the work was already done, and that's why it was really efficient. I'm not sure if there is some unrolling, in fact, forced unrolling inside std reduce. I didn't get the implementation. I just tried to do some measurement to guess what's inside, but I didn't check yet what's inside. Maybe there is one interleaved, but I'm not really sure. Maybe could be other optimization, but maybe one interleaved, it's quite possible. At least on my laptop here, it's better to have 4 or 8. One, it's a good start. Then you can try to enroll and mitigate the problem. But once you enroll, you will just stop to bother the branching predicator. So it's not the same optimization. Okay, Mark said, thanks for the answer and the comparison with Rust. Yeah, of course. Lazy solving, it's really important on all the compilers, in fact. So yeah.
And you have another question for Michael. Have you experimented on the limits of
interleaving? Yeah, I experimented that during my PhD. You have several ways to do that. The first is by hand. Of course, it's not that good. But then there is a limit because you, as Adrien said, you cannot use as much vector register as you want. You have a limit inside your CPU. So if you unroll too much, you will the compiler sometimes will not be really kindful if you ask it to unroll, and will say no, I don't want to unroll, because the compiler knows if it unrolls much, it will get out of the maximum number of vector register it can use. So you can do that by hand, but at some point, if the computing is a bit greater than the reduction, for example, if you do by-center computation, for example, as I did also in my lecture, you will notice that you can interleave less because you have several computing and you have to wait the same amount of time to get the result. So you can overlap a bit more the computing to the waiting time, so you don't have to unroll much or to interleave much. So if the computing is really small, so only a reduction, so only an addition, then it's the worst case. So you have to enroll a lot. But for example, here I enroll 8 times. If I enroll 8 times on my previous laptop, it was not possible because I didn't have enough vector register. So that you have to know well your machine if you want to do it by hand. I did also at some point some code generator to do that for me, because of course it's not unrolling. Unrolling, the compiler can do it for you, but interleaving, it's a bit more complex. And as a developer, you can do it yourself because you know what you are doing, but the compiler cannot do that because it will break the graph of the computing, and the compiler is not allowed to do that. So basically, this is that. If you have enough computation, normally you don't need much interleaving. Maybe once, twice, that I did for bi-center computation or multidimensional bi-center computation. Maybe if I remember, I interleaved only once and it was okay. But basically, you can interleave, and then at some point you will get the same performances, and you say, okay, it's not worth anymore. So.
Michael have had some comments about using execution port and ALP as much as possible.
Oh yeah, for that, generally I ask Macao every time, because it's quite difficult to remember the limit that you can have, and Macao has everything, not in mind, but in in his code. Try also to ask Macao to be sure that you reach the limit, the computing limit, or maybe we have a bit of time, not too much, even if it's not the right one, but I can show you this one. So it's not vectorized, but the problem is not that. Once you get a report from Macao, in the expert part, you will have all the vectorization ratio, efficiency ratio. So here it's a catastrophe because, of course, the compiler does not understand what I want to do. But you get also the assembly here. So I always check with Macao to be sure that I reach the maximum performances of what I want to do. So here it's a catastrophe, but yeah, I will check for that to be sure that I reach 100%. Always a good reflex, not to, because of course if you try or your laptop to try on another server or computing server, it will not be the same. So you ask Macao, and normally should be okay.
You have two questions on performance. The first one is about if you have graphics for performance measuring between STL parallel execution and OpenMP.
Don't have this one. In fact, I do not do both because Sébastien and Vincent are doing the OpenMP part. So I'm doing the STL execution part. But yeah, it could be interesting to see that. But OpenMP is more driven by pragma and stuff like this. So it's not in the language itself, but normally should be quite okay. I'm not sure if you can interleave with OpenMP. Never tried. Unrolling it's okay. Vectorizing it's okay. Parallel is okay. Or maybe OpenSCC also for some tricks could be quite nice. I have to ask Vincent and Sébastien for that. I don't have this kind of graphics yet, but it's a good point. I will try to mix all the results together to have a nice conclusion for the school.
The second question on performance is why we have a big difference in performance between the use of intrinsic and the vectorized reuse.
Yeah, it's because maybe I can show you this one. So if you vectorize with intrinsic, I get exactly this situation. So I use a vector accumulator and I accumulate vector by vector. And at the end of the loop, I reduce my accumulator and I get this value. So the std reduce does the same here. So that's why we get the same performances. But the problem is in the for loop, you explicitly ask for your plus equal here, you explicitly ask for a scalar. The compiler knows that the iteration should return a scalar. So there is this reduce, which is performed at the end normally, if you want to optimize it well, happened inside the loop itself. And that's a big problem in terms of performance. So basically, once you vectorize and what you don't vectorize, you vectorize the load if you are lucky, but only that. There is no vectorized sum here. It's a vectorized sum, but a vectorized sum inside the vector itself. So you still have bad performances here. So that's the main problem because of the graph theory, because of course the compiler cannot change your computing without telling you that there is a problem. So of course, you ask for a scalar, you get a scalar, and for that you need to reduce your vector. You don't want to do that to have performances. But again, if you explicit the order, maybe you need to explicit the order, and the compiler cannot take the liberty to say, okay, there is an ordering, but I don't care of the ordering. It's not possible. So the compiler is really conservative on that. It's normal because maybe some people want to have this order because they sort their data, because they know they are not well conditioned or something like that, as Vincent explained. So you have to have this kind of stuff. That's why the performance is horrible, and you get a 10x difference between the two. But this one is really fast, and you can also unroll a bit, and you can also interleave the bit to be much faster. But this one is just slow, and just the only difference is here you reduce this one, and here you reduce one by one. So you get a small speed up, but not that good. And you get practically a 10x difference between the two. That's the main difference.
Okay. Do you have some more question for Pierre? Perhaps Pierre, you can introduce the next webinar.
Okay, yeah. Yeah, we're on time. It's okay. So next time we will have Vincent again to do some wizardry with Fortran. Fortran on CPU, so CPU computing, everything we can do with Fortran. Fortran, modern Fortran, for Fortran 2023, 2018. So a lot of modern Fortran. And I don't want to spoil too much the webinar, but that's the main idea of the webinar. So to explain to you where do we come from, so the old Fortran, and then the evolution with Fortran IT and Fortran 2023, Fortran 2018, which is really performant, in fact. So if you want to optimize some Fortran, it's a good place to be next week. So we'll do that with Vincent next week.
Perfect. So perhaps Pierre, you can show perhaps the webpage of the Great Scott School just to help people.
You want this one?
Yeah, I give the link. It's just to show again and again to all the attendees. You can have access to all the webinar, and you can directly register on it if you want to assist to one webinar. You have access also to all the program of the Grey Scott School. So if you want to assist to the Grey Scott School, please make the registration. If you want to create a satellite site in your country or in your town, just contact us. Everything is free of charges. So we just have to talk about everything to realize the satellite site. That's all for my point. Pierre, you want to add something?
Yeah, maybe if you want to attend the school in Annecy, just don't wait too much, because place in the hotel are complex to get. So there are still some places in Pré-Saint-Jean, for example. You still have a bit some places, but don't wait too much. Otherwise you will have a problem if you want to come in Annecy. If you are local, of course, there is no problem. But if you are not local, you will have some problem, because the first week of the Grey Scott School will be the same week of the Animation Festival of Annecy, because sometimes we are unlucky and they move their animation festival and we could not move. So a lot of people will need to have an hotel at this point. So we are a bit lucky because we are not in the center of the city. We are a bit far from the center. So normally you should get some places, but don't wait too much for that. Mary wants to open the official registration, normally the 9th of March. So next week, if everything goes according to plan. So don't wait too much to get all the apartment, or you can have an apartment, you can have an hotel, whatever you want, or if you have some family, you can also do what you want. But yeah, don't wait too much, because having some places will be maybe a bit difficult this year, more than last year or the year before. So yeah.
If you have any question, if you need any support to get a room or something like this, or to create a satellite site, or to know how to join us online, etc. If you have any question, just send us a mail and we will help you, of course.
And maybe a point on satellite site. You are not obliged, if you are a satellite site, to follow the 2 weeks. You can get a la carte if you are searching on the first week, on the second week, or only on one topic or another. You can say, okay, I want to form my people, or to form people around, or to make some partnership with other company, or to make just a new partnership. In fact, you can discover new customers with that way, to do some publicity to your computing center. But if you don't have a computing center, it's not a problem anymore. If you have an auditorium and you want to follow the lecture together with other people, you can also say, okay, I want to have a satellite site. It's up to you. the school becomes your school. It's important to highlight that. So you can follow what you want, how you want, with the resource you want, and you can open it to the people you want. So if you want to open or to get close and get only your colleagues and no one else, you can. It's up to you.
So we can close the webinar. Thank you
Yep.
very much, Pierre. I hope to
Thank you,
see
Karen.
you again to the next webinar on Fortran with Vincent. So thank you very much and hope to see you again. Bye bye.
Bye.